Good day, everyone. My name is Falodun Vishel Emmanuel, and I have a presentation today titled The Structural Analysis of a Lightweight Electric Vehicle Chassis. So, this work was done in the effort of Dr. B.V. Onijiji, A.A. Edaniyan, H.A. Wulabi, K.M. Oluwasegun, and O.E. Falodun from the Department of Mechanical Engineering of Obafemi Awolowo University. And this presentation today will cover um, introduction, the objectives, the materials and methods, the summary of our findings, and the conclusion to the work that was done. So for the introductory aspect, we have to consider why we are shifting towards electric vehicles nowadays, why the need for us to use electric vehicles and move away from fossil fuel vehicles. And this is due to the fact that in recent decades there has been increasing and worsening situations of climate crisis, ecological disasters, and rampant pollution. And the scientific community has come together to provide various solutions to it. And one of these solutions is the transition to the use of electric vehicles from fossil fuel vehicles. And this is because transportation is one of the leading causes of CO2 emissions globally, and that's alongside power generation and manufacturing. But it accounts for 28% of the total greenhouse gas emissions globally. And road transportation specifically, that's transportation through cars, trucks, etc. They account for up to 15% of the total CO2 emissions. And things are getting worse every day. Like this year, the global temperature rose by up to 1.63 degrees Celsius, and it has become evident to everybody that using electric vehicles is the way to break out of this terrible situation that we find ourselves in. But for electric vehicles to become more commonplace, some issues have to be resolved, such as the weight of the battery pack, motor, suspension system, and the chassis. The vehicle weight is very important as it helps determine the performance of the electric vehicle. But even with recent developments in battery technology, the energy density of these batteries often limits the performance and mileage of these vehicles. Therefore, to improve the performance of our EVs, some lightweighting has to occur. That means we have to still further reduce the weight of our electric vehicles to put more performance into it. So the problem statement, the objectives of the work that was done. The problem statement: a chassis needs to be able to withstand longitudinal twist, shock, and vibration and other stresses caused by weight, acceleration, braking, road condition, and shock acting on the vehicle. Then the chassis needs to be also be lightweight enough to improve the performance of the vehicle. Then the proposed solution to this problem is to explore other lightweight materials alternatives in place of 304L steel. So explore other alternatives like um, steel, 31L steel, 316L steel, explore other alternatives like some titanium alloys and the rest. So the goals of this is let's move on to the materials and methods that were used for this research. The dimension of the chassis were analyzed, and we used an open source model for it. Then the dimension of the structural members were taken to be 70 by 60 by 2. The entire weight of the vehicle minus the frame was calculated. We are going to use that for static loading simulations. Then using the available information concerning the dimensions of the chassis, the location of the wheelbase, and the height of the height and the center of gravity, the values of acceleration and braking loads were calculated. Then when the values of the static loads, inertial loads and braking loads were calculated, SolidWorks was used to model and simulate the effects of these loads on two models built using 304L stainless steel and titanium 6 aluminum 4 vanadium alloy. Then this was the chassis specification that we used for the open source model. The wheelbase, the dimension of the wheelbase is 2350 millimeters. The track width was 1488 millimeters. The height was 1200 millimeters. Then the material properties of the two materials are in consideration. We took material properties of density, Young modulus, and the yield strength. So the density of 304L steel was 7.9 gram per cm cube. That of the titanium alloy was 4.43 gram per cm cube. The Young modulus was 200 gigapascals for steel, and the Young modulus for the titanium alloy was 113.8 gigapascals. The yield strength for steel was 190 megapascals, and the yield strength of the titanium alloy was 870 megapascals. Then these are some of the summaries of the findings that were taken from the simulation, static loading and all that. So on the slide we have the deformation of the 304L steel chassis. So from the static analysis of the chassis during normal loading due to the weight of the battery and components. So that's simply due to the weight of the battery and components without any passenger on board. We found out that the deformation, the total deformation on the 304L steel chassis was 0.208 millimeters, and the deformation on the titanium alloy chassis was 0.335 millimeters. So this is the simulation for the static analysis of the titanium alloy chassis. The summary of the findings during the static analysis of the chassis during normal loading. This is the second case and scenario that we considered. The static analysis of the chassis during normal loading due to the weight of the battery, components, and passengers. So we took four passengers as the amount of passengers we need to use in the simulation, and we had an average weight of 65 kilograms between each passenger, according to several medical statistics that show that the average weight of a male person in the United States is around 35 kilograms to 80 kilograms. And using applying that weight on the simulation, on the chassis in the simulation, it was discovered that the total deformation was 0.318 millimeters in the 304L steel chassis, and the total deformation was 0.534 millimeters in the titanium alloy chassis. Then we also did another simulation for overload. Overload means some it means it refers to the towing capacity of the vehicle, and we normally add a 20% of the total weight of the vehicle and the passengers to the to the weight that will be used on the chassis to calculate for overload. So overload determines the towing capacity of the vehicle. So under overload, it was discovered that the deformation in the 304 steel chassis was 0.330 millimeters, and the deformation in the titanium alloy chassis was 0.630 millimeters. So yeah, the continuation of this for the conclusion to this work was like the result of the analysis showed that the information
and stresses were found to be under the limit for both materials, and the rate of increase of the volumetric stress and deformation was found to be equal. The result also shows that the total deformation of the titanium alloy is higher compared to the steel foil, but it makes up for it in terms of weight and fatigue strength. And from the analysis, you can see that the deformation for overload cost 0.33 millimeters for the steel chassis, and for the titanium alloy chassis, it cost a deformation of 0.63 millimeters. It was discovered that the total weight of the chassis after of the frame, the chassis itself was for the 304 L2 was 365.56 kilograms, and that of the titanium alloy was 202.25 kilograms. So we arrived at the conclusion that using a titanium alloy chassis brought about a 44.7% reduction in weight, and a reduction in weight means an improvement in the efficiency and performance of the vehicle. So it shows that the titanium alloy is a viable material for lightweighting of EV chassis. But some further studies seem to be carried out in terms of the dynamic